Hello everyone. In this video we are going to talk about numerical solution of differential equations, and this is something like your ODE 45 in MATLAB. So here we're going to use the method called, as you can see here, is called ODE int, and you need to import it from the Scipy integrate sub-library or sub-module, and this one can only solve first order differential equations. So if you have to solve a second order, you have to convert it into two first orders using dummy variables, and I'll tell you. So here, let's say I want to solve a first order ODE where it is like y prime equals negative 3y plus 0.5 sine t, starting from initial condition y0 of 1, and your time vector goes from 0 to 10 with 100 data points. So in order to do that, you have to define a function that gives you the right-hand side of the first derivative. So this guy here, it should be a function that receives t and y as input and speed out this function. So here you define it, give it any name that you want. It takes y and t and gives you back negative 3y plus 5 sine of t, and of course numpy sine of t. And then you pass this function to ODE 45 to give you the y prime to that. You give it the initial condition and the time vector. And then this is going to give you back the y values where you can plot it versus what? Versus time here. And let me go ahead and run this for you. So this is the plot of this function here, right? And this is a linear ODE. There is analytic solution for it, but you can make this function as complicated as you want and make it in a case that there is no analytical solution for it. So you see here, there is a numerical solution, and then again, for this case, there is analytic solution because it's linear, but I can always go ahead and make it nonlinear, let's say by something like this. If I make this a square, right, then I can add y terms and anything else to it. And let's see what happens if I just, out of curiosity, make this 3y squared. Is that going to make it? Yes, it is going to make it unstable. And this system is unstable right now, and of course the solution is going to be crazy big at one point. So here, let me go back to that linear term, but instead I'm gonna get rid of this sine term, so it is gonna be an exponential decay basically, right? So if I get rid of the forcing function and it's just y prime equal negative 3y, then the solution is e to the negative 3t times initial condition, so I should expect it to exponentially go down. And let's see if it does. It should, right? And you see that it is exponentially going down, and after so many seconds it's practically zero, right? So you see that it is clearly doing its job for you over here. And as I said, you can make it as complicated as you want. Now if you have a second order ODE, like for example a pendulum, you know, for a pendulum the theta double prime equals negative g over L sine of theta. So here, instead of theta, I'm using y, but it doesn't matter. You can name it whatever you want. And here, this is g over L, right? So your L is roughly about 2 meters, right? If you say g is 10. And here I have added a damping term, negative 0.5 omega to it. So the pin of the pendulum has a damping. So if you start from some angle and let the pendulum go, you expect this behavior to be kind of periodic. It's not exactly periodic. You know, there is no analytic solution to this second order ODE because it's nonlinear. It has this sine of y term in it. And it's what we call quasi-periodic. There is no analytic function for it. You have to resort to numerical solution for this. And because of this damping, the energy of the system will go out, so your harmonics start to damp out, and finally the system will go to rest. And the bigger this coefficient is, the faster the system oscillations will damp out. So what you need to do is to, since this is second order, my ODE int method is not gonna handle it. So I convert this into two first order ODEs. And here I define two dummy variables, z1 and z2, right? Which are coming from the input z. So this z is a vector basically, and it has two inputs, Z1 and Z2, where Z1 in here, if I want to add something for you, your Z1 is the same as Y, and your Z2 is the same as dy over dt, or theta and omega in this case. And so your Z is going to be the vector of Z1 and Z2. Now, if I do that, since Z1 is Y, if I take a time derivative from both sides of this, I get d of Z1 over dt is going to be dy over dt, but dy over dt, based on definition, that's equal to Z2. So you see the right-hand side of this first order ODE, if you forget about this part, right? Let me add the parentheses here. The right-hand side of this first ODE, first order ODE, is Z2. That's why I have it over here. And then if I go ahead and let me add this to this side, and maybe add that explanation over here for you. And the second dummy variable is dy over dt. Therefore, the time derivative of z2 with respect to time is going to be second time derivative of y with respect to time, which based on your ODE is going to be this, right? And it's going to be equal to what? Well, now get rid of this part and add it down here, an extra explanation. So now, what is it? Well, negative 0.5 dy over dt. dy over dt itself is z2. So it's going to be negative 0.5 z2, right? Of course, with an asterisk. And then negative 5 times what? Sine of y. But y is what? Y is z1. So if you look at the right-hand side of the second ODE, which is also first order, this one, and this portion, you see the right-hand side is negative 0.5 z2, negative 5 sine of z1, which is what you can see over here. So these two components of dz over dt, they are the right-hand sides of my first order ODEs. One of them is this guy, the other one is this one. And those, as I said, will define the right-hand sides. So now this is the output, which I'm going to return for this function. And finally, I call my ODE int with this function. I pass to it an initial condition, which in this case, there are two numbers in it. Why? Because I have two components in the z, right? So I have to pass the initial condition for this. And so I have to have z1 at 0 and z2 at 0. z1 is theta, so I use pi over 3 for it. So I release it from 60-degree angle, and z2, which is initial omega, I release it from rest at 0. So I'm going to move the pendulum to 60 degrees and let go. And I solve it for 10 seconds with 101 data points. So I pass the time vector to it. I pass a z, and let me call this tt vector if you don't mind. So that is different from the t of the input of this function, although it's not going to affect it by any means. Get my solution. Now the solution, which is z, has two basically components, z1 and z2. That's why you see here when I'm plotting basically what? All the rows and the first column, which is theta or y, and then I plot the second column, which is omega. So I plot theta in blue, omega in green, give them a label so I can use my legend later, and give it X label, give it a title, and then finally show both of the outputs. So let's go ahead and run this one. and that is going to give me the second plot, as you can see, and you clearly see there is oscillation, and you clearly see it is going to damp. If you wanted to see that it's almost going at 0, what you can do is you can bump up this number here, right? So let me make it 0.8 instead of 0.5 to make it faster for you. And you can probably give it more time as well, right? Then you are kind of sure that it is gonna damp out, and it is going to be what? It is gonna be just fine. So let's go ahead and run it one more time for you. It should definitely be a faster decay, and you see, there we go. They're almost going to be 0 after about 10, 11, 12 seconds or so. The motion of the pendulum completely stops if you look at theta. Okay, so here you see I solved a first and a second order ODEs, linear, nonlinear, doesn't matter. With the ODE int method, showed you the results, and hopefully this video is useful to you. So I will see you in my next lecture. Thank you.